Light stands as one of the most transformative innovations in human history. The journey began with the invention of the incandescent light bulb. Over time, the fluorescent light bulb became the star and replaced the incandescent light bulb. Today, LED takes the lead, bringing brightness and efficiency together and changing how we see the world. In today's video, we are diving into the fascinating world of LED lights, its structure, and working function. LEDs are versatile and can be found in various types in our daily lives. These are called through-hole LEDs. This is an LED bulb, featuring surface-mounted LEDs inside it. LED stands for light emitting diode, a semiconductor device that emits light when an electric current is applied. The process is based on electroluminescence, where the movement of electrons within the semiconductor material generates photons, producing visible light. First, we will clarify what is this diode. A diode is a two-terminal electronic component that allows current to flow in one direction, forward biased. This is a diode where the anode is positive and the cathode is negative. When connected to a battery with the positive terminal to the anode and the negative terminal to the cathode, forward bias, current flows easily through the diode. However, if we reverse the battery's polarity, reverse bias, the diode blocks the current flow in the opposite direction, maintaining its one-way behavior. It is primarily made of semiconductor materials, such as silicon or germanium. This is through-hole LED. Let's explore how this LED works. It has anode lead and cathode lead, reflective cup, semiconductor die, wire bond, lead frame, positive terminal and negative terminal. Here, the semiconductor is the main part. The upper part is called P-type, and the lower part is called N-type. Now we have to understand the P-type and N-type. In silicon, there are 4 valence electrons located in the outermost shell. These valence electrons are involved in covalent bonding with neighboring silicon atoms, forming a crystal lattice structure. Each silicon atom contributes 1 electron to each of the 4 covalent bonds it forms with adjacent silicon atoms. Here, no free electron. These are boron atoms, each having 3 valence electrons in the outermost shell. Now, if you replace 1 silicon atom with a boron atom, which has only 3 valence electrons, there is a deficiency of 1 electron in the crystal lattice. This deficiency is referred to as a hole. This type of semiconductor is a P-type semiconductor, where positive charge carriers, holes, contribute to the electrical conductivity. When a silicon atom is replaced by phosphorus in the crystal lattice, an extra electron is introduced, creating a free electron. This results in an N-type semiconductor, where free electrons become the dominant charge carriers, contributing to electrical conductivity. When we combine a P-type semiconductor with an N-type semiconductor, we create a PN junction. This junction is where the P-type and N-type materials meet. If you connect the positive terminal of a voltage source to the P-type material and the negative terminal to the N-type material, this forward biasing reduces the potential barrier at the junction, allowing charge carriers, holes from the P-type and electrons from the N-type to move across the junction more easily. During this time, electrons are released protons and light emitting. If you found this video helpful, don't hesitate to share your thoughts in the comments below. Thank you. Let's grow up, never stop learning.